Well, oh well. Use your imagination for the last 7 minutes. Yeah. All right. So, okay. So that's h prime of t. Now we need to calculate, for the sake of putting together this Taylor's theorem, we need to calculate h prime prime of t, right? So how do you take the second derivative here? We've got h prime prime of t. So look, we've got h1 times d dt of f sub x of g of t. See that? And then plus h2. That h2 is just a constant. So d dt of f sub y of g of t. Right? Now we're looking at a composition of f sub x and f sub y. These are functions of two variables, right? So we have to do the chain rule for those, each one of those. And so what we're looking at is h1 gradient of f sub x at g of t dotted with g prime of t, all times h1, plus h2 gradient of f sub y at g of t dotted with g prime of t. Now, of course, g prime of t is very stupid. It's just the vector h1 comma h2, right? So this works out to h1 times like f sub x, excuse me, f sub xx at g of t, right, times h1 plus f sub yx at g of t times h2 plus h sub 2 times f sub xy at g of t times h1 plus f sub yy at g of t times h2. All right? So let's put this all together. What does this give us for h prime prime of 0? It simply gives us h1 squared fxx of p plus 2 fxy. Oh, let me write the h1 second. Sorry, guys. 2 fxy of p, h1, h2, and then plus fyy of p times h2 squared, right? All right, so let's put it all in. Let's put it all together here. Actually, so you have to go back here and imagine taking my expressions for, h of 0. What is h of 0, by the way? That's just f of g of 0, also known as f of ab, which I'm abbreviating as f of p, right? Okay, so if we go back over here and we look at h of 1, well, that's going to give me f of p plus f sub x of p times h1 plus f sub y of p times h2 plus, well, f sub xx, my bad, of p times h1 squared plus 2 fxy of p times h1 h2 plus f sub yy of p times h2 squared, all divided by what? 2, right? Plus dot 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 dot. But what is h of 1? H of 1 is exactly f of g of 1, right? Which in particular is f of a plus h1 comma b plus h2, right? And this right here is the multivariate power series expansion for a function of two variables, just up to quadratic order. So we've seen before the linear piece of this. That's just the tangent line, tangent plane approximation to z, right? So like, if I swap out, I don't know, I mean, this is fine. Nothing wrong here. This is equal to that, all right? But maybe it's a little bit prettier if I rewrite it in terms of like, x and y. So what we have is that f of xy is equal to like f of a comma b plus fx of a comma b times x minus a plus f sub y of a comma b times y minus b plus, I'll factor the half out, 1/2 fxx of ab times x minus a squared plus 2 fxy a comma b times x minus a times y minus b plus 1/2 fyy of a comma b times y minus b squared. And then plus higher order stuff. And that right there is really all I wanted to derive for you guys today. This right here is the multivariate power series expansion for a function of two variables to quadratic order. And this pretty much has in it everything we need for like optimization of a function of two variables. This is the main story. See, because you already know this piece right here, if we put z equals to this, this set equal to z is what? Z equals to this stuff is what? That's the tangent line, right? Tangent space, rather. Not line. What's wrong with me here? That's the graph of the tangent space, right? The tangent plane, I should say. Tangent plane. It is, after all, a plane here, right? But what's that? Well, that's the best quadratic approximation, you see? The best quadratic approximation to the function near the point AB, right? So next class, we'll use this because you guys think about this. What happens if we're at a critical point? Critical point what has what? It has the x derivative and the y derivative are both what? Remember? They're both 0. So the value of the function is totally dominated by this quadratic form right here, right? But at the end of last class, I showed you guys that we have complete understanding of what happens to a quadratic form if we simply analyze the so-called characteristic equation of it that I derive through that laborious Lagrange multiplier derivation, right? So we'll actually work that out next class, and I'll derive what's known as a second derivative test. But anyway, for the rest of today, I just want to talk about the concept of a multivariate power series. So let's do that. I mean, this right here, this is a multivariate power series, right? It's just an unending polynomial in several variables. So like, let's try another one. Suppose I had f of x comma y z equals to 13 plus 3x minus z, plus xy plus, I don't know, let's say yz squared. So this would be an example of a multivariate power series, right? In this is a function of three variables, right? And if we think through this, we can understand all kinds of information about the function from the coefficients of the expansion. For example, what is f of 0? What's the origin? F of the origin. What's that? 13? Okay. Everyone agree? Why do you agree? It's pretty obvious, right? If you plug in 0, the only thing that survives is 13, right? What happens if we take the x derivative of this? Like, what's f sub x of this? 3 yeah, plus y, plus stuff, whatever, right? What's the y derivative? X plus z squared, all right. And what's the z derivative? Negative. Plus, not y, but 2yz, right? Plus stuff, all right. So from those three things I just wrote, you guys tell me, what's the x derivative at 0? What's the y derivative at 0? What's the z derivative at 0? And I'm using 0 as a vector here, if you guys don't mind. I'll tell you what, I'll adorn it with a vector. Does that make that's better? Okay, there. I made it vectory. So we get what? We get what? We get 3, 0, and negative 1. So in other words, the gradient of f at the origin is 3, 0, minus 1. So that tells me, among other things, that the origin is not a critical point, right? I can see from just looking at the power series expansion that the first derivatives of this function, they're not all 0 at 0. In other words, the origin is not a critical point. How about if I calculate, like, you know, fxx, fxy, f, you know, xz, fyz, fzz, right? There's, in this case, check this out, right? There's not just 3 seconds, for a function of 2 variables, we only had 3 mixed partials to consider, right? xx, xy, and yy. If we have 3 variables, there's 6 partial derivatives to consider. Do I have them all? xx, xy, x. Oh, fyy. Thank you. So how does it go? xx, 0, xy. Well, 0 plus dot, 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 right? I mean, I don't have the full story here. Yeah? xy, what do we got? It's 1, right? It doesn't matter which one you differentiate. Remember the Clairaut theorem, the partial derivatives commute? Xz, 0, right? Yz, looks like we got a 2z there. Zz, looks like we got a 2y there. Yy, 0, all right. So there you go. Those, and of course, like, then you can evaluate this at 0. See, the second derivative at 0 is 0. I mean, I don't really know for sure, since there's a plus dot 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 here, and here, that it's actually strictly 0. However, if I plug in, right, if I plug in the origin, then all of that higher order stuff, it dies, yeah? And so we actually do have full confidence in saying that we've got 0 there. In fact, the only thing that's not 0 is what? Yeah, just the xy term is the only non-zero piece there. Yeah.
Why does f of xy not have the dot dot dot? And also.
Oh, it should. It absolutely should. Thank you. That's a very good question, and the answer is I'm not thinking clearly. You're right. It's just I get a maybe not quite a passing grade on my plus dot dot dots. I had 4 out of 6. That's it's like a D. I guess it depends if I need this course for like future credit or not, right? Whether that counts for me.
Also, why is that equation
Uh-oh.
that the last variable have a half from it?
Oh, that's interesting. Yeah, no. Sorry. I already got my half out here. All right. So there's a pattern here, right? And so like the trivariate series looks like this, guys. I don't know if I've got room to write it all out here. put it here just so you have it juxtaposed against the second order one. So if I have a function of 3 variables, the multivariate power series, at least to start with, looks like, you know, f of the point, and let's say the point's ABC. So it's f of the point plus f sub x of the point times x minus a plus f sub y of the point times y minus v plus f sub z of the point times z minus c, right? And then plus 1/2, parentheses here, fxx of the point times x minus a squared plus 2. Let me do the double ones first. It doesn't really matter which order you write it in, but f sub yp of y minus b squared, f sub zz of the point times z minus c squared, and then you've got 2 fxy of the point times x minus a times y minus b plus 2 times fxz of the point x minus a times z minus c plus 2 fyz of the point y minus b y minus c. All right, close big parentheses, and then there's higher order stuff. That's what happens for 3 variables. And the derivation would be very similar to what I showed you at the start of class. It's just, since you've got 3 variables, you get 6 terms when you multiply out a trinomial times a trinomial, and you group like terms. You have 9 total terms, 6 of those grouped together in groups of 2. Now, there's a kind of like a better way to write this. So if you'll forgive me for a brief journey into linear algebra land here for a second, it helps. What you're looking at here is fxx, fxy, fxz, fxy, fxz, fyy, fyz, fyz, fzz, that matrix times like the vector x minus a, y minus b, z minus c times this vector x minus a, y minus b, z minus c. This is a way of writing what I would call the quadratic approximation, the quadratic piece in the approximation for f. That all of this jazz right here is this. It can be written like that. Yeah.
For this very last term,
Uh-oh.
should be y minus b and c minus c.
Yes. Well, let's see. I think 1, 2, 3, 4, 5, 6. So I think I got like a B, like a mid B on this one. If we count the subparts though, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I got like a 92. Sorry, I'm an idiot. Let me stop. But yes, that's supposed to be Z. Thank you. Are there anything else? Okay, so like long story short, in Math 221, we eventually learn that this is a symmetric real matrix, and as such, it's orthonormally diagonalizable, which means that we get complete control over what the formula can be rewritten as in terms of eigencoordinates. But this is a story I have to tell you in Math 221. This is just a shout out to that, all right? I'll stop right there for that. That I will not test on that in here, obviously. Okay, so the question then is, for us, how do we find multivariate power series, right? And so at the moment, what I've done is I've just given you one, and I've asked us to try to understand what the meaning is of the numbers, right? So let's do another one, see if you can tell me the meaning of the numbers. But I want to do this time, I want you to tell me the meaning of the numbers without actually differentiating. All right, do you guys understand the task here? So I'm going to give you a power series. I want you to tell me the values of the derivatives without actually differentiating. And let's do it something other than the origin for a change. So suppose you're given that f of x y z is equal to 67 plus 13 times x minus 1 plus 20 times y minus 2 squared plus 30 times y minus 3 times, oh good grief, y minus 2, I'll get it eventually guys, times z minus 3. All right. So my question to you is, can you tell me, I'm just going to ask about some select ones, what's f of 1, 2, 3? What's f sub x of 1, 2, 3? What's f sub y of 1, 2, 3? What's f sub z of 1, 2, 3? What's f sub yy of 1, 2, 3? And finally, what's f sub yz of 1, 2, 3? We should be able to answer these just by matching the pattern. All right, just pattern matching. We don't actually need to differentiate. When I ask this question on the test, I inevitably see people differentiating because they haven't really learned the pattern matching, which is unfortunate, because that's part of what I'd like you to pick up on here, is just that we can read directly from this derivatives and values. So like, first of all, f of 1, 2, 3 is what? You guys said it. Let's see here. Sorry, this is my children's fault. F sub x is what?
13.
13? Did you guys agree? Yep. All right. F sub y?
0.
0. Very good. It's not there, right? Like the wings on an elephant. Z also 0. F sub y.
20.
20 is incorrect. So this we have to think about. This is f sub y of 1, 2, 3, right? Divided by 2 is 20, right? So we get what? We get 40. Now, this guy, on the other hand, we have, notice how it works out. You see the half and the 2? They'd be canceling, right? So this is, in fact, literally f sub yy, my bad, yz of 1, 2, 3 equals to 30. Oh, so it's 30. All right, great. How about all the other mixed partials? Like, what is f sub x? Like fxx, fxy, fzz. How about those? What are those? Those are all 0 and under the assumption, of course, that this is the end of the story in terms of the quadratic expansion, right? Everything past here is like cubic order or higher. Since there is no xx term, there is no xz term, there is no yy term, right? Etc.
There is a y.
Oh, there is?
Yep.
Oh, man. Oh, I did that already. ZZ. All right. All right, there we go. Okay. All right. Enough about interpretation. How do we construct multivariate power series? How do you guys think we're going to do it? The answer is almost never. So what I have on the middle board here, these are the analogs of like Taylor's theorem for multivariate, right? These are the multivariate Taylor theorem for n equals 2, the multivariate Taylor theorem for n equals to 3, just a second order. Now I do have formulas in the notes for arbitrary order, and I'll probably mention those next class. But what I want to talk to you about now is something actually much easier, which is how do we create multivariate power series? And the answer is more often than not theft. Theft, you say? Yes, theft. Theft from calculus 2. All right, so here I have to assume some things, namely that you know some things, What things do you know? Well, you know the Maclaurin series expansions for exponential, for sine, for cosine, for cosh, for sinh, for those expressions which are connected to the geometric series, right? So like, let me see here. Example 4. So rather than restate those, let's just use them, and maybe you'll get the idea here soon enough. Suppose I want to find, so I have f of xy equals to 1 over 1 minus x squared, and I'll put a y up top. There we go. So what I can do here is I can go, this is a geometric series with a equals to y and r equals to x squared. So in other words, the multivariate power series expansion here is just n equals 0 to infinity of, like y x to the 2n. So the way that goes is y plus yx squared plus yx to the 4th plus ... There it is. The thing I used here was the geometric series. Do you guys remember the geometric series? I'll remind you, in case you forgot. A over 1 minus r is equal to the sum, n equals 0 to infinity, of a r to the n. This is the geometric series. Of course, that's a plus ar squared explicitly, right? This is the geometric series. When does it hold? Yeah, we need for this to converge, we need that the absolute value of r is less than 1, right? So like this calculation I did for x and y, it's only going to be legitimate when like the absolute value of x is less than 1. But there it is. So you guys could answer a host of questions about this function now with this power series, right? Like what's the, what if I calculate the 300th derivative of f with respect to x? I can't. Is that the right notation? Yeah. At 0. Now, I know I haven't written the general power series expansion, right? But where that data is going to be paired to is with x to the 300 without a y. There is no such thing in this expansion. Therefore, this is 0. There's no x to the 300 term in the expansion. So that's kind of neat. Do you guys remember these problems in Calculus 2 where I ask you to like calculate the 100th derivative of a function by using the power series working backwards? Yeah. Okay, another example. What if we had f of xyz equals to, let us say, x squared plus y times the sine of z. Well, what I can do here is, you guys remember the power series expansion for sine? What was it? So we go z minus 1/5 z cubed, and then plus higher order stuff. Right? That's the Maclaurin expansion for sine, plugging in z. And then the power series for this example, you just multiply out. Simple as. So like here I have, let's see here, the lowest order term would be yz. And then I'd have like plus x squared z minus 1/5 x squared z to the 3rd power, and then higher order stuff. There you go. That's the multivariate power series expansion for this up to 5th order. Now, if you tried to calculate this directly from the theorem I haven't stated, you'd have to calculate a stupid number of partial derivatives evaluated at 0, right? That is obviously not the way to do it. Just like in Calculus 2, it's rarely the case that direct use of Taylor's theorem is the appropriate way to find the power series expansion for a function. More often than not, substitution's the way, all right? Substitution into a known result. Another example. Up till now, these examples have been like relatively benign. We try to come up with something a little bit more spicy. Uh-oh, what'd I do?
For example 5, like why don't we have the term -1/5y?
I missed something? -1/5 what? Oh, negative, yeah, that is actually there, isn't it? And it belongs, oh man, I get I'm at 75. So yeah, y, man, that's a good thing I'm not taking this for credit today. YZ cubed, and then minus, then the thing I wrote, -1/5 x squared z to cube, is that right? All right, yeah, so maybe I should write down all four, all four products, right? Yes, uh-oh.
Why is it a fifth instead of a third?
Oh no, a fifth instead of a third. Oh, that's a good question. I think it's because I skipped an important step, which was to remind you guys that the sine of u is u minus 1, thank you, third u cubed plus 1/5 factorial. Wait a minute, is it 1/3? Oh no, now you guys have got me doubting. Wait a minute, isn't it, it's 3 factorial, isn't it? Oh goodness gracious. Those are not 5s, those are what? Those are 6s. Oh, it's much worse. Yes, let's try to remember the power series. See, I need to teach Calc 2 again, apparently. All right, there we go. 6s all around. All right. Let's try another one. Maybe I can not make a dumb error this time. Example 6. What if we were up against, let's say, f of x comma y equal to the sine of 1 plus x squared plus y squared. Oh, I don't like that. It's too bad. That's too ugly. Let me try xy instead. That's only marginally horrible. There we go. So something like here, I think the first thing you want to do is use the adding angles formulas for sine and cosine, right? So like, this is what? This is sine of 1 cosine of xy plus cosine of 1 times the sine of xy, right? Now, let me try to do this one right. Cosine of u is what? 1 minus 1/2 u squared 1/4 factorial u to the 4th plus dot 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 dot, right? So here, explicitly, we have the sine of 1, and then that's 1 minus 1/2 xy squared plus stuff, cosine of 1 times, okay, sine of u was what? That's u minus 1/6 u cubed plus stuff, right? So making a substitution for u equals to xy here, for the sine of xy term, we have xy minus 1/6 xy quantity cubed. Okay, so altogether, let me clean it up. we've got sine of 1, and then plus cosine of 1 times xy, and then minus 1/2 sine of 1 times x squared y squared, minus 1/6 cosine of 1 times apparently x cubed y cubed. And there you go. That's the multivariate power series expansion for sine of 1 plus xy up to order 6. Let me again point out the obvious, that if you were to use the theorem I haven't stated in here and try to construct the multivariate power series simply by partial differentiation, it would have required the calculation of a stupid number of partial derivatives. This is like way, way easier substitution. All right? Do you guys remember any other power series? E to the x. All right, so suppose we have f of xy equals to e to the, let's say x squared plus y squared. What should I do here? Again, so at the moment I'm just trying to find the expansion about 0. All right, maybe tomorrow we'll look at one that's not around 0 a little bit, but the exponent, I like that. So this is e to the x squared times e to the y squared, and then that is like 1 plus x squared plus 1/2 x to the 4th plus dot 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 dot. Likewise, 1 plus y squared plus 1/2 y to the 4th plus dot 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 dot. Y to the 4th power. I'm doing what? I'm making a substitution. I'm substituting into e to the u is 1 plus u plus 1/2 u squared, all right? So if I make a u equals x squared, and so if we multiply this out, we've got 1 plus x squared plus y squared plus, well, higher order stuff. So with this alone, you guys tell me, does this function have a local minimum or a local maximum at the origin? And what is the value at the origin? You can see it right here, right? It's 1. Are there any x derivatives or y derivatives here? No. There's no x or y term, so this is a critical point because it starts at quadratic order. And because we got pluses in both terms, we can just analyze it with intuition. Think about it. If we're not at the origin, we're adding something to 1. So the values get larger away from 1. Therefore, it's a minimum. It's a local minimum. Now, I can't do that kind of easy reasoning if there's a mixed term, right? If there's a mixed term, we need something else, and that's what we'll talk about tomorrow, is the second derivative test. But before I do that, I'll try to run through a few more examples of these just to make sure we're all on the same page. It would be good for you to read the notes and remind yourself all the power series stuff you guys have forgotten, because,